This is week 4 of the applied thermodynamics problem solving session. So, previous weeks we started with the vapor power cycle. So, we started with the vapor power cycle and we saw Rankine cycle, and the second week the idea of the Rankine cycle, the components used in Rankine cycle, how it's different from a Carnot cycle, and we compared both of its efficiency and how the Rankine cycle is lacking. Then we saw how can we improve the efficiency of Rankine cycle by adopting a reheat or regenerative process, and or increasing the pressures. So how each of it is affecting the cycle and how it's affecting its efficiency, and the practical aspect, how the limiting case, basically the vapor fraction, so how it's getting affected when we are employing one of its these variations to the Rankine cycle. So that was on Rankine cycle. So we will see on the components side now. So major components which we have is starting with is a pump. So is a pump, the centrifugal or some other type of pump which can use. So that, and then you have a boiler where you are adding heat and converting the water to steam. So that is one of the major component, and the other component is the turbine. Then where you are expanding the steam and producing work out of it. So that, if you see, the turbines comes in majorly two types. One is reaction turbine and there's an impulse turbine. Then after turbine, you see you have again condensing heat back. So you need a condenser. So these are the major components of an Rankine cycle. So we'll see each of it in a brief, small, try to connect out in small short time, give an introduction of this, and then we'll move on to see some problems of this. So as I told, turbine can be of two types. One is impulse turbine and another is a reaction turbine. So the figure to the right shows you the two diagrams of it. So first is an impulse turbine. So if you see this rotor, so that is your turbine which is rotating and it's producing work. So that is mounted with moving buckets. So a cross section of this is given down. You see this green colored portions is the nozzle through which your pressure is converted into high velocity steam. That steam goes and hits the blade. So that impulse is what is driving this turbine. So hence it's called an impulse turbine. So this is the buckets which is mounted on the rotor. So the nozzle which is fixed, so from there the high pressure steam is flows through this nozzle, gains velocity. So we see at the bottom, so this purple line or blue line is your steam pressure. So initially the pressure of the steam is at high. When it goes through the nozzle, this pressure drops. So the pressure drops when it goes through the nozzle, and then by that time the reduction in pressure is converted into kinetic energy, or it gains velocity. So there's increase in velocity. So at the exit of the nozzle you have maximum velocity and minimum pressure. So this goes and hits the blades of the turbine and the turbine rotates. So here the pressure drop is only across the nozzle. So but what happens in a reaction turbine? So reaction turbine, there is no more a fixed nozzle. So across the turbine, because of the fluid which is coming out, because of the velocity differences and so on, your turbine blade will make it to rotate. So here if you see, there are two parts. One is fixed blade and then one is a moving blade. So in fixed blade, what happens is the pressure drops and there is a velocity gain. So as shown in the diagram below. So if you see, again the pressure drops in the moving blade and velocity is gained, and then again in the moving blade what happens is there is again pressure which is drop, and there is also velocity drop, which is both is converted into your moving of the turbine to generate work. So in this case, if you see, there's maximum utilization happens in case of a reaction turbine compared to an impulse turbine. So your reaction turbine is much more efficient compared to an impulse turbine, but impulse turbines are generally used for smaller capacity work where it is required, and reaction for a higher capacity works. So if you see, the pressure drop, all pressure drops in the is occurring in the nozzle and no pressure drop in the blades. But in a reaction turbine, pressure drop occurs both in nozzle as well as in the moving blades. And one more difference which you can see is the impulse turbine, you have such a bucket kind of blade, or a conical, I can say concave surface kind of blade in a impulse turbine. But in a reaction turbine, you have similar to an aerofoil shape. So if you see, the driving force is the impulse effect of the steam jet, which is driving the impulse turbine. But in case of reaction turbine, you have both impulse effect and the reaction force, which is driving the reaction turbine. So impulse force is because of the fixed velocity gain in the fixed nozzle, and moving blade is because of the reaction force which is generated out of the velocity with the velocity with which the fluid is coming out. So that is creating an opposite reaction force which is driving the turbine. So that both plays a role in creating work. So in impulse turbine there is a high jet velocity, high blade velocity, but in reaction turbine there is low jet velocity and low blade velocity. So what is degree of reaction? So if you see, in the reaction turbine there is a term called degree of reaction. That is nothing but the enthalpy drop across the moving blade divided by the total enthalpy drop across the fixed blade and the moving blade. So that is called as the degree of reaction. So it's a comparison of this thing, both the turbines. So pressure drop, as I told, there is only in nozzle, not in moving, but here in both the blades there is a pressure drop. So area of blade channel is constant, but it's varying converging type in case of a reaction turbine. So blades, as I told, it's a profile type or the concave kind of surface. Here in reaction turbine it's an aerofoil type. So admission of steam, this not all round or complete. Here it's all round and complete. Here nozzle, the outside you have a diaphragm which contains the nozzle, but in case of reaction turbine, fixed blades similar to moving blades attached to the casing serve as nozzle and guide to the steam. So you have both fixed and moving blades attached to the casing, which will act as a nozzle. Power, so not much power can be developed in an impulse turbine, much power can be developed in a reaction turbine. Space wise, this requires less space for same power, and a reaction turbine will require more space for the same power. Efficiency wise, impulse turbine is low and reaction turbine has high efficiency. Suitability, suitable for, as I told, is for small power requirements and suitable for medium and high power requirements. And blade manufacture, it's not difficult for a profile type, but it's kind of difficult for a reaction turbine. So now we saw this turbine, but this turbine uses nozzles to increase the velocity to create an impulse effect. So we'll go on to see nozzle. So before seeing nozzle, so we need to know a term called sonic velocity. That's the maximum speed of sound you can get in a straight tube. So the speed of sound. So sonic velocity in a fluid is given by c is root of dp by d rho, or can write for idealized fluid gas gamma RT. Then Mach number is nothing but your velocity compared to your sonic velocity. So velocity by your speed of sound. So if it's less than that is if velocity is equal to speed of sound, it's called sonic, and if it's more than the speed of sound, it's called supersonic, and if it's less, it's called as subsonic. So can straight away finding m, we can find out which kind of flow that is. So flow through a nozzle can be written as this: dA by A equals m square minus 1 into dV by V. So in case of your Mach number less than 1, so this term in the bracket becomes negative. So your velocity, to have an increase in velocity, you need a decrease in area dA. So dA should be less than 0 for you need higher velocity at the exit. So when you are in subsonic flow, the converging passage will give you a nozzle that is increasing in velocity, and diverging passage will give you a diffuser. So that will reduce your velocity and increase your pressure. Sorry for the interruption. There was a network issue. I hope now it's sorted out. As I was speaking, so if Mach is velocity is less than 1, that is, it is subsonic flow, then my decrease in area will create an increase in velocity as per this equation. This comes from the state energy mass balance equation, and then it will act as a nozzle. If there is an increase in area, then my velocity will start decreasing, and it will act as diffuser. Sorry again. Let me reshare. Okay. Uh, so I was speaking. So similarly, when we are in case of a supersonic flow, that is when Mach number is greater than 1. In that case, this bracket term will be positive. So you need a increase in area to create a increase in velocity. So in supersonic, when Mach is greater than 1, so a diverging nozzle will act as a nozzle, and a converging passage will act as a diffuser. So similarly, to increase from a subsonic flow to supersonic flow, you need a converging and diverging nozzle, and you will have a Mach number of 1 at the throat. So moving on to boilers. So boilers, you can have two types. So one is a feed water. So as I went back, so boilers, one is water tube boiler and fire tube boilers. So here, so basically the name itself says what exactly that is. So in tube you have water passing, then that will be a water tube boiler. If you have flue gases passing, then that is your fire tube boilers. So the first one is a fire tube boiler. So what happens is, you have a tube in shell and tube heat exchanger thing. So the shell part will have water, and you have multiple tubes which are pouring inside the shell, and then that carries the hot flue gases from the furnace. So you heat and burn something, so that gases which are at a very high temperature will be passed throughout the tubes, and that in turn will get cooled down through the passage of tube, and it will pass the heat to the energy to the water, and the water will in process boil and produce steam. So that is a fire tube boiler, and the other is the water tube boiler. So similar scenario, but you have water which are passing through the tubes and gases which are passing on the outside of the tubes. So hot flue gases through the tubes heat the water on the tube in the container. It takes more time to start steam generation after firing the boiler. So this disadvantage with the hot fire tube boiler is it takes too much time to start steam generation, and the rate of steam generation is lower. Fourth is generates low pressure stream up to 20 bar. And fifth, this is suitable for heating in chemical process and also as process steam. The second is a water tube boiler. Water, in this case, water passes through the tube and heats it's heated by the hot gases around the tube. So this takes less time compared to the previous fire tube boilers, and similarly the rate of steam generation is higher. It generates high pressure stream up to 200 bar, and this is suitable for high capacity power generation. So similarly, so this position, as I have already told, what is a fire and water tube, and mode of firing is generally internally fired, and this is externally fired. So the fire is outside and flue gas is inside. So that basically In operating pressure, so operating pressure is limited to 16 bar in terms of fire tube boilers, and it can go as high as 100 bar. So steam production is very lower, and in water tube boilers is higher. Suitability, it's not suitable for large power plants. As I told you, it can be used to generate process steam and so on in some chemical plants. But this water tube boilers are suitable for larger power plants. So risk of bursting, so involves lesser risk on explosion due to lower pressure, and involves more risk on bursting due to high pressure. Floor area, so for a given power it occupies more floor area, and this occupies a very low lesser floor area. The construction part is difficult in case of fire tube boiler and simpler in water tube boilers. And shell diameter is large for same power, so as flow area is larger, so eventually your heat reaction size will also be larger and smaller in terms of water tube boiler. The treatment of water not so necessary, and this is necessary because tubes you can have fouling and that will reduce your heat transfer capacity. And then accessibility of various parts. Various parts are not so easily accessible for cleaning, repair and inspection. These are easily accessible. So with that we can, and the condenser part is mostly you have a similar kind of this thing. If you have a water cooled or some to cool your to condense the steam, or you can basically use what is called as cooling towers are generally used to condense the steam. So where you pour the water from the top and you pass air, so some part of water gets evaporated and the water condenses, that energy is taken away from the water itself and the water basically cools. So that is the principle of an cooling tower. So with that we will move on to some problems and MCQs. So starting with, in an impulse turbine the dash 4 statements is given, so we need to state which one is true. Absolute velocity at the inlet of moving blade is equal to that of the outlet. Relative velocity at the inlet of the moving blade is equal to that of the outlet. Axial velocity at the inlet is equal to that of the outlet. Whirl velocity at the inlet is equal to that of the outlet. So we need to find out which one. So the answer is B. Relative velocity at the inlet of the moving blade is equal to that of the outlet in case of an impulse turbine. So the answer is B. In Mollier diagram, constant pressure lines dash from one another, maintain equal distance, diverge, converge, nothing can be said. So Mollier diagram nothing but an HS diagram, enthalpy and entropy diagram. So what happens to constant pressure lines? So this is how a Mollier diagram looks like. So you have enthalpy on the y-axis and entropy in the x-axis, and this green lines you see are temperature lines, constant temperature lines, and these red lines are constant pressure lines, and this blue line is your constant vapor fraction lines. So if you see these red lines compared to a lower temperature, at higher temperature the gap between two lines are more, so this are basically diverge. So in Mollier diagram, constant pressure line diverge from one another. So answer is option B. So we have two statements. You have to see which is true. The question is, nozzle control governing cannot be used in reaction steam turbines. Reason: in reaction steam turbines, full admission of steam must take place. So both A and the options are both A and R are individually true, but R is not the correct explanation of A. B is both A and R is true, but R is the correct explanation of A. The option C is A is true, but the reason is false. The option D is A is false, but R is true. So for our case, both are true, but R is not the correct explanation of the statement. So both of the statements are individually true. Nozzle control governing cannot be used in reaction steam turbines. So because we need to in reaction systems, we also fully admit the steam must take place. So we cannot govern by using nozzle. So if you put some control over the nozzle to control the steam, how much is going the nozzle, so that will hamper the performance. So that is not the ideal way of controlling a reaction steam turbine. So option A and R are both are correct statements, and A is the correct R reason is the correct explanation for A. So moving on. Next statement is impulse staging is commonly employed in high pressure part, and reaction staging is intermediate low pressure parts of the steam turbine. Reason: the tip leakage across moving blade is less in impulse staging, as the pressure drop is small and there can be a large pressure drop across fixed blades and nozzle. So similar statements, we have to see what is true and what. So here too, both the statements are true, and the reason is the correct explanation for A. So impulse staging is used where high pressure part is present, so that will create an increase in velocity, and at lower pressure you use a reaction staging. So the reason is what is stated, and that is true. So moving on to the next question, consider the following statements in respect of impulse steam turbines. The first one, blade passages are of constant cross-sectional area. The second is partial admission of steam is permissible. Third is axial thrust is only due to change in flow velocity of steam at inlet and outlet of moving blade. So which of the statements given above is correct? So the answer is all three statements are correct. So in impulse steam turbine, your blade passages does not change. So we discussed this at the start when we comparing impulse and reaction turbine. The reaction turbine, the blade passages changes, but there's a constant cross-sectional area in terms of impulse steam turbine, and there's partial admission of steam is permissible. This again you have a nozzle control for controlling your impulse steam turbine. Then axial thrust is only due to change in flow velocity of steam at inlet and outlet of moving blade. So axial thrust is the axial velocity. So the difference in velocity is what is causing the change. Thrust. So the next is a water tube boiler has dash compared to a fire tube boiler for the same diameter and thickness of tube. A, less heating surface. B, more heating surface. C, equal heating surface. D, heating surface depends on other parameters. So we saw water tube boiler and fire tube boiler. So sizes of the boilers also we have come to see. So with respect to that, if you see, so in water tube boiler, water is contained in many smaller diameter tubes. Therefore, the heating surface of water tube boiler is more than that of the fire tube boiler. The relatively large heating surface of the water tube boiler increases the evaporation rate. So that is the reason. So it has more heating surface area. Though the water tube boiler is smaller, but in terms of surface area for heating, since there are multiple tubes and the water is contained in those tubes, so the surface area is more for water tube boiler compared to a fire tube boiler. So next is a flow through a nozzle is regarded as A, constant volume flow, B, constant pressure flow, C, isothermal flow, and D, isentropic flow. So the answer is D, isentropic flow. So you assume that entropy across the nozzle is constant, so you assume it to be an isentropic flow. Next is because you also assume that it to be a reversible adiabatic process, so hence isentropic flow. Thermodynamically efficient process would involve dash exergy loss with dash rate of entropy generation. So thermodynamically efficient process, so it should have minimum exergy loss and minimum rate of entropy generation. So it's both are same. So if we have minimum entropy generation, that will cause minimum exergy loss. So exergy loss, you say the total exergy loss will be T naught into delta S generated. So both are same. So both will have a minimum for to have a higher efficient process. So next question is, the pressure at which the steam leaves the nozzle is known as back pressure. So it's true or false question. So the answer is true. So the pressure at which the steam leaves the nozzle is known as back pressure. Next is, if at inlet of the turbine the water possesses kinetic energy as well as pressure energy, the turbine is known as reaction turbine. So the answer is again true. In kinetic in impulse turbine, you convert whole of the pressure energy to velocity in terms of kinetic energy, and that goes and impinges the blades, and that impulse is what drives the turbine. But as we saw in the reaction turbine, you have both pressure energy as well as kinetic energy, which is used to run a reaction turbine. So answer is option A, true. So next is in an impulse turbine, in reaction turbine, the heat drop in fixed and moving blades are 39 kilojoule per kg and 40 kilojoule per kg respectively. The degree of reaction for the stage will be, so this is easier. They are given how much the heat drop across the moving blade and the fixed blade. So just 40 and 39 kilojoule per kg. We need to find out the degree of reaction. So degree of reaction is nothing but your drop across the moving blade divided by the total drop. So here it will be 40 divided by 40 plus 39. Sorry, this is 30 kilojoule per kg. I think there's a typo here. So 30 kg and 40 kg. So 40 divided by 40 plus 30. So this will come out to be 4 by 7. So answer is option A, 4 by 7. So let's move on to some problems. So the question is, consider a steam power plant operating on the simple ideal Rankine cycle. So steam enters the turbine at 3 megapascal and 350 degrees Celsius and is condensed in the condenser at a pressure of 75 kilopascal. So heat is supplied to the steam in a furnace maintained at 800 Kelvin, and waste heat is rejected to the surrounding at 300 Kelvin. So determine A, the exergy destruction associated with each of the 4 processes and the whole cycle, and B, the second law efficiency of the cycle. So what we know is, we know the inlet to the turbine, which they have said it is at 3 megapascal and 350 degrees Celsius, and they have also given us the condensing pressure, which is 75 kilopascal, and they are saying that so furnace temperature is also given, which is at 800 Kelvin, so that's a heat source temperature, and they are saying in the condenser surrounding temperature is 300 Kelvin. So this is all what we know. So using this, this is how the cycle will look. So the pump is pumping to 3 megapascal from 75 kilopascal, and then where we are heating it to convert it to steam, which we don't know, we have to calculate, and what we know is the exit 3 megapascal and 350 degrees Celsius. and that is run in the turbine, and it comes at 75 kilopascal and rejecting heat to the ambient at 300 Kelvin. So this we can plot in a TS diagram. So this is a usual case which we saw in the previous week's episode. So we know the inlet. So from there we draw an reversible adiabatic process. So isentropic process, the entropy is same, 275 kilopascal, and then we can estimate the vapor fraction there using the 75 kilopascal saturated liquid and saturated vapor entropies and the entropy at the inlet of the turbine. So that gives you vapor fraction using which we can estimate the enthalpy. So there we can estimate the enthalpy here. Next is okay, from there then we know saturated liquid enthalpy which is pumped at 75 kilopascal. So now we know enthalpy exit of the turbine and enthalpy into the pump, so we can find out the Q rejected to the condenser. From this saturated liquid, then we can estimate via minus V dP, we can estimate the enthalpy at exit of the pump 2, and we know enthalpy at state 3, so we can estimate the heat which is added in the boiler. So heat added which will come out to be 2729 kilojoule per kg, and the work done in pump, that is specific volume into the change in pressure, will come out to be 3 kilojoule per kg, and similar turbine out is 713 kilojoule per kg, and your heat rejected is 2019 kilojoule per kg. So this all is what we can find from an ideal Rankine cycle, and the efficiency, thermal efficiency, will be 26%. That is 713 divided by 2729 will come out to be 26%. So from here, the first part is we need to find out the exergy destruction which is associated with the 4 processes. So what we know is 1 to 2, 3 to 4 are isentropic process. That is the compression or the pumping process, and in the turbine, because it's an ideal Rankine cycle, both are isentropic process. So there will be no irreversibilities because your entropy is constant. There is no entropy generation. So both internal as well as external irreversibility are 0. So your exergy destroyed is which is T naught into delta S, that will also be 0. So process 2 to 3 and process 4 to 1 or constant process pressure heat addition and constant pressure heat rejection. So this will have internal reversibility. So because you have a say a temperature difference for which the heat transfer which has to take place, so this will be an irreversible process. So we can find out the entropy of stream at each of the states. So just like how we found out enthalpy, we can find out entropy. So S1 will be equal to S2 and S3 which is equal to S4. S1 is nothing but a saturated liquid entropy at 75 kilopascal. So that is equals to 1.2132 kilojoule per kg Kelvin, and similarly your entropy across the turbine is 6.7450 kilojoule per kg Kelvin, because we know that entropy at inlet of the turbine is at 3 megapascal and 350 degrees Celsius. So using this we can write an exergy balance across the condenser. So this will look like something like this: T naught S3 minus S2 minus Q in divided by T source. So this is what we get. So this is can do it an direct exergy balance, or you can do an entropy balance, and you will both end up with the same equation. So T naught is 300 Kelvin, and we know the entropies. So substituting that, and we know how much heat we are giving to the cycle, which is 2729, and we also know the source temperature of the furnace, which is at 800 Kelvin. So substituting that, we will find that the exergy destroyed across the boiler is 636 kilojoule per kg. So that basically says that we are losing 630. If we are using the same heat to generate work, we are losing this much amount of work. So similarly, in case of condenser, T naught is at 300 Kelvin. So S1 minus S4, similarly Q out by your sink temperature is again your ambient temperature. So this will come out to be 360 kilojoule per kg. So the total irreversibility or the total exergy destroyed in the cycle is just the summation of all. So exergy destroyed will come out to be 996 kilojoule per kg. So the other way round of finding the exergy destroyed is T naught into your source temperature based on the surrounding entropy which is generated, Q out by TL minus Q in by TH. So this will also give you the same value. This is calculated based on the process. So if you, this is based on the surrounding, if you apply, so you'll get the same. So the largest exergy destruction in the cycle occurs during the heat addition process, which was 636. So if we want to reduce the exergy destruction, so we have to start with the boiler to see how we can bring down that exergy to improve the exergy efficiency of the whole cycle. So this can be done by raising the turbine inlet temperature. So this will reduce the temperature difference and thus exergy destruction. So that is one way of doing. So basically you are moving the cycle up. The second is to find out the second law efficiency. The second law efficiency is nothing but exergy is recovered divided by exergy expended, or you can say 1 minus exergy destroyed by exergy which you are spending. So the exergy which by heat is 1 minus T naught by TH. This is the exergy which is spent or given to the cycle. So 1 minus T naught by TH Q in. So this will give me 1706 kilojoule per kg. So that exergy expended is exergy heat in plus the pump work. So 1706 plus 3, which is 1709 kilojoule per kg. Out of which how much we are recovering is 713 kilojoule per kg. So substituting that, we'll get 713 by 1709, or the other way around is we can use just substitute the exergy destroyed, which we have already calculated, 996. So 1 minus 996 divided by 1709. So both will give me 41.7%. So this basically says that compared to a Carnot cycle, my cycle Carnot cycle is 100%, my cycle is 41.7%. So it's a comparison to a Carnot cycle. Any doubts in the previous problem? Okay, so moving on, we have steam which is entering a converging diverging nozzle at 2 megapascal and 400 degrees Celsius with a negligible velocity and a mass flow rate of 2.5 kg per second. So we have a converging diverging nozzle, and okay, so you have a converging diverging nozzle and your inlet is at 2 megapascal and 400 degrees Celsius. So and your velocity is negligible. So it has given mass flow rate is 2.5 kg per second, and the back pressure or the exit pressure is given as 300 kilopascal. So now they are saying that flow is isentropic between the nozzle entrance and throat, and the overall efficiency is 93%. First is to determine the throat and exit area, and B, the Mach number at the throat and the nozzle exit. Okay, the sides are jumbled up. Okay, so A, since the inlet velocity is negligible, so the inlet stagnation states is identical to the so stagnation state is when you bring the velocity to 0, so that becomes your stagnation state. So that is identical to your static state. So the ratio of the exit to inlet stagnation pressure is, so P2 by P01 is 300 kilopascal divided by 2000 kilopascal, which comes out to be 0.15. So this equation for a throttle, to find out the critical pressure ratio, is P star by P naught equals 2 by gamma plus 1 or K plus 1 raised to power K by K minus 1. This is 0.546. This becomes 0.546 because for a steam it's 1.13. So substituting K value there, it will come out to be 0.546. So if you see, our velocity is much smaller than the critical pressure ratio. So for this, so my our pressure ratio, so if P star by P naught, so P naught is 2000, so P star should be at higher pressure. Our pressure is much lower. So this basically says that my exit condition is at supersonic. So if you have a converging diverging nozzle, so which is given in our problem, so converging diverging nozzle, so at throat you will have a sonic velocity, and that pressure ratio is what is given as 0.546. So my pressure ratio is much smaller than 0.546. So there is again reduction in pressure, which will increase the velocity. So in the diverging nozzle, again there is a gain in velocity, and it goes to supersonic condition. So my exit will be for sure in a supersonic state. So at throat, my pressure will be 0.546 into the inlet pressure. So it will come out to be 1.09 megapascal. So this is all what is known. So inlet pressure 2 megapascal and temperature is 400 degrees Celsius. So corresponding to this, we can estimate the enthalpy, which comes out to be 3248.4 kilojoule per kg, and entropy is 7.1292 kilojoule per kg Kelvin. So now at throat, similarly my entropy is same, and I know the pressure, so I can estimate the enthalpy is 3076.8 kilojoule per kg, and my specific volume will come out to be 0.24196 meter cube per kg. So we have found out at two states. So initially I know pressure and temperature, then I know pressure and entropy, and I have estimated the enthalpy and velocity from the steam table. So next is using this I can find out the velocity. So velocity is just an first law. So your h plus v square v square by 2. So plus gz equals to constant. So here inlet velocity is negligible. So the exit velocity will become root of 2 into the change in enthalpy. So your velocity at the throat is, because we are considering the inlet and throat, so the throat velocity becomes 2 into 3248.4, which is the inlet enthalpy, minus 3076.8, which is the exit enthalpy, will give me 585.8 meter per second. So this is the sonic velocity. So the flow area at the throat is determined from the mass flow rate relation. So I know the mass flow rate, I have estimated the specific volume, so and I know the velocity. So using this I can find out the area of the throat section. So area into V is nothing but the volume flow rate, and m dot into specific volume is again volume flow rate. So I can estimate area. So that comes out to be 10.33 in 10 power minus 4 meter square, or 10.33 centimeter square. So now at exit is given as 300 kilopascal, and my entropy is also same, is 7.1292. So I can estimate the enthalpy which comes out to be 2783.6 kilojoule per kg. So, but what is given is the enthalpy of this, the nozzle is 93% efficient. So, your nozzle efficiency is defined as inlet enthalpy minus exit divided by inlet enthalpy minus the ideal enthalpy at exit. So, substituting here, I can find out the exit enthalpy, which comes out to be 2816.1 kilojoule per kg. So, using this P and H value, I can estimate the specific volume again. So, this comes out to be 0.67723, and entropy is 7.2019 kilojoule per kg Kelvin. So, again now I know enthalpy, I can estimate the velocity at the exit. So, using the same relation, so velocity will come out to be 929.8 meter per second, and similarly area I can estimate as 18.21 centimeter square. So, second is to estimate the velocity of sound and the Mach number. Class enactable and mail IIT Wi-Fi guys. Half an hour. Sorry. So, the velocity of sound and Mach number at throat and exit of the nozzle are determined by. So we know. So estimate velocity of sound. C is nothing but root of dou P by dou rho at constant entropy. So this, when we convert into an exact differential, it is delta P by delta rho, and we know rho is nothing but inverse of specific volume. So delta P by delta 1 by specific volume at constant entropy. So velocity of sound at throat is determined by evaluating specific volume at the constant entropy condition of 7.1292 for pressures of 1.15 and 1.065. Because we don't know the value for the exact pressure, so we take at 2 and we extrapolate it, and substituting there, delta P is 115 minus 1065 kilopascal divided by the specific volume at these two pressure points and the entropy value, which is 1 by 0.23776 minus 1 divided by 0.24633. So these are the specific volume estimated at the pressure and the entropy value. So this comes out to be 584.6 meter per second. So if you see previously, this is what we got in the relation. So 585.8. So close. This is because we are approximating it here. So Mach velocity is 1.002. So that is basically 1. So at throat, and we also know that in a converging diverging nozzle, you get Mach 1 or sonic velocity at the throat. So the flow at the throat is sonic as expected. This is because of replacing derivatives with the differences. So that is the because the numerical error which you are getting. So next is the velocity of sound. Similarly, we can estimate at the 300 kilopascal at exit. So again we are taking plus 25 and minus 25. So and estimating the, we know entropy, which is 7.2019 kilojoule per kg Kelvin at the exit. So using that entropy and this pressures, we estimate this specific volume, and substituting that, we'll get in the velocity of sound as 515.4 meter per second. So Mach number becomes velocity by speed of sound, which is 1.804. So as we told, the exit should be a supersonic condition. So that's what we found. So this is at supersonic velocity. So in this case, we know that the process is in an adiabatic process. So two things we found out. Using nozzle efficiency, we found out exit enthalpy, and then at the throat section, we found out the critical pressure, which is equals to 0.546 times the inlet pressure. So using this pressure and entropy values, we estimated enthalpy, and we applied an energy balance to find out the velocity. and using velocity estimated the area. So, and we cross verified with finding out the speed of sound at each of the points, the throat and the exit, from the stream table. So, any doubts in this question? Okay, so I'll move on to the next question. So, this question, so we have a steam turbine which develops 184 kilowatt with a consumption of 16.45 kg of steam of kg per kilowatt hour. So, the pressure and temperature of the steam entering the nozzle are 11.8 bar and 220 degrees Celsius. The steam leaves the nozzle at 1.18 bar. The diameter of the nozzle at the throat is 7 millimeter. Find the number of nozzles if 8% of total enthalpy drop is lost in friction in diverging part of the nozzle. Determine the diameter at the exit of the nozzle and exit velocity of the leaving steam. So, there are too much stuff which is given here. We will break it down step by step. So, what is given is there is a steam turbine and we know the exit, we know the work which is generated, the power which is generated, which is given as 184 kilowatt, and to develop that 184 kilowatt, there is the steam which is consumed is 16.45 kg per kilowatt of hour. So, for generating 1 kilowatt hour of work, the turbine consumes 16.45 kg of steam. Next, they are saying that to this turbine, the steam is entering from the nozzle entering to the nozzle at 11.8 bar and 220 degrees Celsius, and the steam leaves the nozzle at 1.18 bar. So, across the nozzle we know the pressure and we know the inlet temperature, and they are saying the diameter of the nozzle at throat is 7 mm. So, this is the description of the nozzle. Then they are saying we need to find out the number of nozzles such nozzle is used. Then they are saying in the diverging portion of the nozzle, so it's in converging diverging nozzle, that in the diverging portion it has 8% enthalpy drop due to friction. So, we need to find out the number of such nozzles used, the diameter at the exit of the nozzle, that is the divergent portion at the exit. So, what is the diameter there, and then the exit velocity of the steam. So, this is how it will look. So, in a HS diagram, so at state 1 is at 11.8 bar and 220 degrees Celsius. So, that is the inlet to the nozzle, and then ideally it should be an isentropic process. So, your entropy should be same. So, at state 2, which is your critical pressure ratio or the throat section where sonic velocity is 1. So, till there it's in isentropic process. So, there if you see that pressure comes out to be 6.43 bar. So, just like similarly previous, like we substitute there, and inlet pressure is 11.8 bar. So, if you substituting that, it will become 6.43 bar. So, from there again it expands in an diverging portion of the nozzle. So, ideally it should reach state 3 assuming entropy is constant. So, in that case an exit pressure of 1.18 bar, but they say there is a 8% drop in enthalpy. So, it reaches state 3 dash. So, this is what exactly the process occurring across the nozzle. So, as I told, we know this all the data. So, power consumed, power developed in the turbine, the steam consumed, and steam entry pressure, steam exit pressure, and diameter at nozzle throat. So, and the throat pressure is 6.43 bar, which we have calculated. So, using this we can find out H3 dash is this is again from just like the nozzle efficiency. So H3 dash is 2857 minus 1 minus 8 by 100. So that basically says 92%. The nozzle efficiency is 92%. So they have indirectly given that 8% loss in the nozzle is occurring at the diverging portion. So that basically says the diverging nozzle is 92% efficient. So this is what you will get. H3 dash is 2857 minus 92 by 100 into 2857 minus 2460. So 2857 is the inlet enthalpy and the exit enthalpy is 2460 ideally. So the entropy is constant and you know the pressure, so you can estimate the enthalpy at state 3, and using these two enthalpies we can find out state 3 dash, which comes out to be 2491.7 kilojoule per kg. So steam flow rate is given in terms of kg per kilowatt hour. So substituting we can estimate the total steam which is consumed. So mass flow rate is 184 into 116.45. So this comes out to be kg per hour. So converting that into second, we divided by 3600. So the mass flow rate is comes out to be 0.8407 kg per second. So steam consumption is known in terms of kilowatt hour. So we multiplied with respect to the power which is generated, and with that we converted it into kg per second. So now we know mass flow rate. We can estimate just like in the previous case, we can find out the velocity and then specific volume. Using specific volume, we can find out the area, or if we know the area, we can find out the number of nozzles. So now we know throat area at state 2. We know mass flow rate. So we can find out the number of nozzles which are used. So state 2, we know the entropy, which is same as state 1, and we know the pressure across the throat is 6.43 bar. So using that we can estimate the enthalpy there as 2749 and specific volume as 0.3 meter cube per kg. So using that we can find out the velocity at throat, which comes out to be 44.72. This is to convert the kilojoule to that will come out to be 44.72. Here it's kilojoule per kg. So substituting that, so we can the kilojoule per root of 1000 becomes 44.72 into the delta H. So this comes out to be 464.7 meter per second. So m dot is again area into velocity, which is the volume flow rate, divided by the specific volume into the number of nozzles. So using this we can find out the number of nozzles as it comes out to be 14.04, so approximately 14. So we are using 14 nozzles to run this turbine. So now we need to find out the velocity at exit. So similarly we know the exit enthalpy. So the exit velocity we can find out 2 root of 2 into h2 minus h1, so h1 minus h2, inlet minus exit. So it comes out to be 854.4 meter per second. So now we know the exit velocity and we know the mass flow rate, so we can estimate I think the slide is missing, so I will give you how to solve this. So we know the velocity at exit, we need to find out the diameter of the exit. So that is nothing but you have to find out the area basically. So the same expression will be used. So m dot into v2 by a2 into velocity into n. So from this we can find out the area. So here m dot will be same, n we have already found out. So specific volume at exit will come out to be 1.4 meter cube per kg. So in this case we know at exit enthalpy, we know exit pressure, so we can estimate the entropy and specific volume. So it is 1.4 meter cube per kg. So substituting that here, we can find out the area at the exit of the nozzle. So from there we can find out the diameter, which is just 5/4 d square. So that to cover the nozzle part. So the major part is in nozzle is the critical pressure ratio, which is 0.54 or 2 by gamma plus 1 by gamma minus 1, gamma plus 1. So that is the part. With that we can basically solve the nozzle problems. So next is to coming out to the boiler. So we estimate the boiler capacity. So the question is, we have a 10 megawatt steam turbine which operates with the steam at the inlet at 4000 kilopascal and 400 degrees Celsius, and the exhaust is at 10 kilopascal. So 10 tons per hour of steam at 300 kilopascal is to extract for process work. So isentropic efficiency of the turbine is 75% throughout. Calculate the boiler capacity. So what we know is shown in the diagram here. So TS diagram. So you have at inlet to the turbine, which is at 40 bar and 400 degrees Celsius. From there you are expanding. So ideally comes out to be state 2s, but this being not isentropic process, because isentropic efficiency is given as 75%, this comes to be state 2. From there you are taking some part of the steam for some other process work, which is not needed, but in a plant you take away some part of the steam for other processes. So here this part of the portion is not, we have to see how much is, we have to calculate how much of it is used. Here so again the rest of the steam which is left. So initially the steam which is passing to the turbine is Ms. From there M portion of the steam is taken away, and rest Ms minus M amount of steam is again expanded in the turbine to come to state 3, which is at 10 kilopascal, which is sent to the condenser. So we need to find out the boiler capacity to generate this Ms amount of steam. So how do we estimate this Ms? So we know 10 tons of hour per steam is required for process work, which is given 10 tons of so M is given straight away, it's given M. So M is 10 tons per hour, so 10 into 10 power 3 is 10,000 kilojoule per 10,000 kg per hour, and the capacity of the power plant is given as 10 megawatts, which is again 10,000 kilowatts. So the power which is generated in the turbine is, if we see in the diagram, is Ms into H1 minus H2, then Ms minus M, where because the M amount of steam is taken away, that the rest of the portion is Ms minus M, which is expanding from state 2 to 3. So Ms minus M into H2 minus H3. So that is what is written here, Ms into H1 minus H2 plus Ms minus M into H2 minus H3. This gives you the total capacity of the power plant, the work which is generated. So that is 10,000 kilowatt. So here we can estimate the enthalpies at each of the states. So inlet enthalpy H1 is at state 40 bar and 400 degrees Celsius. So that comes out to be 3215.9 kg kilojoule per kg, and the entropy is 6.7743. So using this entropy we can estimate state 2s. So that is equal to state 1 entropy. So from there we can estimate the entropy at state 6, entropy at state 2s. We can estimate the vapor fraction, we can estimate, and then correspondingly we can estimate the enthalpy at state 2s. and using the efficiency of the turbine. So here we have estimated the vapor fraction at state 2s, which comes out to be 0.9592, and the enthalpy using the same relation, we can find out enthalpy at state 2s as 2636.5. So now using enthalpy of the turbine, which is 75%, we can estimate the change in enthalpy H1 minus H2, which comes out to be 434.55 joule per kg, and individually enthalpy H2 is 2781.35 kilojoule per kg. So as we can see from the steam table, so this H2 enthalpy will be greater than the saturated steam enthalpy. So this says that it is in superheated state. So from superheated state we can estimate the entropy at that point, which comes out to be 7.08 kilojoule per kg, and temperature is 170 degrees Celsius. So basically it's state 2. So from there we can again estimate the vapor fraction at state 3s, and that comes out to be 0.857, and using that we can estimate the enthalpy at the exit H3s ideal case. It will be 2242.46. So again you are applying that efficiency of the turbine to estimate the change in enthalpy as 404.17, and the absolute enthalpy at exit is 2377.18 kilojoule per kg. So now we have estimated all the enthalpy values. So only unknown here is the mass of steam, m dot s. So substituting it here, it comes out to be and rearranging it comes out to be 13.263 kg per second. So or 47745.2 kg per hour, or 47.745 ton per hour. So this is the capacity of the boiler which is required, because this the boiler has to supply this much amount of steam for the plant to generate the 10 megawatt of power. So any doubt till now? This is the last problem which I have for today. So if you have any questions you can ask. I'll move on to the next question. Okay, so the last question is, we have a steam at 70 bar and 450 degrees Celsius is supplied to a steam turbine. After expanding to 25 bar in high pressure stages, it is reheated to 420 degrees Celsius at constant pressure. Next, it is expanded in intermediate pressure stages to an appropriate minimum pressure, such that part of the steam blade at the pressure heats the feed water to a temperature of 180 degrees Celsius. The remaining steam expands from this pressure to a condenser pressure of 0.07 bar in the low pressure stage. So the isentropic efficiency of high pressure stage is 78.5, while that of intermediate and low pressure stage is 83% each. From the above data, determine the minimum pressure at which bleeding is necessary, the quantity of steam bleed per kg of flow at the turbine inlet, and third, cycle efficiency. You can neglect the pump work. So this is how the cycle looks like. So what is happening is you are pumping the fluid from state 6 to state 7. So where it is going to the feed water heater. So the feed water heater is at 180 degrees Celsius. So if you see 180 degrees Celsius, because this is at pure fluid, so your pressure will also remain same. So that will come out to be 10 bar. So at 180 degrees Celsius it will be at 10 bar. So from this feed water heater, again you are pumping it back to the boiler. So in the boiler you are converting that into steam, and you are superheating, so on, and then you are passing it to the high pressure turbine. So high pressure turbine, you are expanding to some state, and then you are reheating it again, and sending it back to an intermediate pressure turbine where you are expanding and some portion of it is bleed to send it to heat the fluid. Then the remaining is sent to a low pressure turbine, and the low pressure turbine expands to state 5. So this is what is happening. So just the turbine portion is given in the HS diagram. So 1 to 2, then so 1 to 2 dash is actual process, and then 3 to 4 is the ideal in the intermediate pressure turbine, and the actual is 3 to 4 dash, and then 4 dash to 5, and the 4 dash to 5 dash is the low pressure turbine. So we can see how to solve this. So as I told, the feed water is heated at 180 degrees Celsius. So corresponding to that, the saturation pressure will be 10 bar. So thus the pressure at which bleeding is necessary is at 10 bar. So the intermediate pressure where we are bleeding it is known. Now it is at 10 bar. So straight away the first question can be answered straight away. So now we need to estimate the enthalpies at each of the point. So H1 is known, the inlet condition, which is 470 degrees Celsius and 70 bar, and then they have given second stage is expanding to 25 bar. So second intermediate pressure we know 25 degree and 420 bar. So we can estimate state 3, and H2 we can estimate using the isentropic process. So we can find out H2, and 2 dash we can find out using the efficiency of the turbine. We can estimate 2 dash. So H3 minus again H3 minus H4 is 0.83 into H3 minus H4. So from there we can find out the efficiency H3 minus H4 dash, so which is 207.5, and H4 dash the same process we can estimate till state 4 and 4 dash. So using 4 dash we can estimate the entropy and then find out enthalpy at state 5, and using the efficiency formula we can estimate the state 5 dash. So that's what is happening next. So we know we have found out H5 using an isentropic process. So in a HS diagram you can straight away find out in the steam table also, and then using that we can find out the actual efficient enthalpy H5 dash, which is 2356.6. So we have found out all the enthalpies across the turbines. Next is the quantity of the second question is the quantity of steam inlet bleed per kg of flow at the turbine inlet. So if we do an energy balance across the feed water heater, because that whatever mass is bleed from the turbine is used to heat the fluid coming from the condenser. So if you put up energy balance across the feed water heater, so m kg of heat is coming at 10 bar at state 4, and then it is going at state 8, the saturated liquid at 10 bar, and then from pump inlet is 1 minus m kg, this is coming at state 7. So we know HF7 we can calculate, which is the saturated liquid at state 6, which is 70 kilopascal. So from there V delta P we can estimate enthalpy at state 7, and then enthalpy at state 8 is known, saturated liquid at 10 bar, and then the inlet enthalpy at state 4. So that also 4 dash we have calculated. So H4 m dot into H4 dash plus 1 minus m into HF7 equals HF8. So this is the energy balance which will come across the feed water heater. So now substituting all the enthalpies, we can straight away find out the mass which is bleed, which is 762.6 minus so the enthalpy value. Substituting it come out to be 0.206 kg of steam flow at turbine inlet. So if 1 kg of steam flows through the turbine, so you are extracting 20% of the steam to bleed in the feed water heater. So using this, now we can find out the cycle efficiency. So we know all the enthalpy values. So work done is the work generated in each of the turbine. So 1 into H1 minus H2 plus 1 into H3 minus H4, which is the intermediate turbine, and from there m portion of the steam is bleed. So the last turbine, your mass flow rate is 1 minus m. So 1 minus m into H4 dash minus H5 dash divided by the total heat added. So H1 minus HF8 plus H8 minus H3 minus H2. So the total heat added is between state 9 and 1 and 2 and 3. So substituting all values here, enthalpy values will come out to be 36.83%. So the efficiency of the cycle here is 36.83%. So this is a combined problem of both the reheating and the regenerative cycle. So I thought it's a bit tougher than what we saw in the previous week. So I thought I'll have this also in today's class. So any doubts? With that, I finished what I've prepared. If you have any doubts, you can ask. Okay, then if you have no doubts, we can. Thank you. So then we can end the session. Thank you for joining. So next week we'll start with I think gas power cycles. So this was a vapor power cycle. So this week ends with vapor power cycle. So next, because here we are operating in the two-phase dome. So if we are operating at above the two-phase dome, so that will be a gas power cycle which we'll be covering in the coming weeks. So thank you for joining. See you next week.